All right, in this video, I wanted to talk about section 6.2, which is about exponential functions. And so the first thing I'm going to do is just to play around with an exponential function or two and see how it behaves. And let's just pick, for no good reason, let's just pick the function 2 to the x. So what I want to do is I'm going to pick some inputs, which I'll call x, and then I'm going to consider what's the effect on the function 2 to the x. And let's look at just a few values just to plug in. So say -3 to 3, just the integers between -3 and 3. And if I plug in -3 to the function 2 to the x, f of -3 would be 2 to the -3. So f of -3 is 2 to the -3. And remember that that's 1 over 2 cubed, or 1/8. And likewise, 2 to the -2 is 1/4. 2 to the -1 is just 1/2. Anything to the 0 is 1. Almost anything to the 0 is 1. And 2 to the 1 is 2. 2 squared is 4. 2 cubed is 8. And so what happens is you get a function that's going to look roughly like this. So I'm just going to plug in these values here. So we're going to say 2, 4, 6, 8. And when we have -3, we have about 1/8. These get really hard to make precise, but you'll get the idea. At -2, we have 1/4. At -1, we have 1/2, 1, 2, 4, and 8, doubling each time. And then the curve y equals 2 to the x is going to be what we get when we kind of connect the dots in a smooth way. It's a continuous function. It's going to look roughly like that. Okay, so that's y equals 2 to the x. And then we could do something similar if we had another function, say y equals 1/3 to the x. I'm just going to compute a few values here, but it'll be the same idea. And I want you to notice actually one thing before I move on to a new function. Notice that for y equals 2 to the x, that the larger the power you take, the function goes to infinity. And so the way that we can say that precisely is that the limit of 2 to the x as x goes to infinity is infinity. So the larger the input, the larger the output, and it gets arbitrarily large. On the other hand, when we go the other direction, when we keep taking half and half and half and half, the values get arbitrarily small, but they're always positive. So this is an important thing to note for exponential functions in general. 2 to the x is always positive. In particular, it's never 0 and it's never negative. Okay, so it's always positive. And you could get this to be as small a value as you like, but it's never going to equal 0. Okay, and that'll be important for us later on. On the other hand, when we take the limit of 2 to the x as x goes to -infinity. Okay, so as x gets large in the negative direction, the values get very small, and this becomes, this approaches 0. Okay, so the limit of 2 to the x equals 0 as x goes to -infinity, but it's never equal to 0. Okay, so just something to keep in mind there. All right, next let's look at y equals 1/3 to the x, or if you like, you could think of this as 3 to the -x. And this is going to have a similar pattern when we have inputs x. I'm just going to do a few values here. Say -2, -1, 0, 1, 2. Okay, when we plug in -2 to this function, we're going to get 9. When we plug in -1, we'll get 3. And then when we plug in 0, we'll get 1. When we plug in 1, we'll get 1/3. When we plug in 2, we'll get 1/9. And when we graph this function, we're going to end up with something that's going to, I'm not going to be very precise here, but this is going to look something like this. Okay, so as x increases, so the limit as x approaches infinity of 1/3 to the x is going to be 0. And the limit as x approaches -infinity of 1/3 to the x will be infinity. Right, as x gets large and negative, the y values get, as x gets large and negative, the y values get large and positive. Okay, so this is going to go to positive infinity. Okay, and so that's basically everything that you need to know about the graphs of exponential functions and what they look like. Basically, there's two types of exponential functions that we're going to study. And we're going to study this when a is positive. So when of course, when a is positive, but when a is bigger than 1. And that's going to be the functions that go to infinity. So like 2 to the x. Or we could have a being between 0 and 1, in which case it's going to be like the 1/3 to the x, where the function will decrease in asymptote to 0. Okay. But again, and I can't stress this enough, a to the x is never going to equal 0. It's always true that a to the x is positive, okay, for all x. Okay, for all x. As long as it's defined, it's positive. Now, you can't have negative values, and you can't have 0. So it's not defined. 0 to the 0 is slightly tricky. Okay, so we'll see that 0 to the 0 is not a well-defined limit. You can't have a negative value. So even just -1 to the x is not a well-defined function because, for example, how could you deal with, so just to give you an example of the type of problems that you could come across, let's think about -1 to the, let's see, -1 to the 1/2 is undefined, right? Because it's the square root of -1, and that's already a problem. But what if you had -1 to the, let's say, 4/2? Okay, now you have not only the problem of -1 to the 1/2 existing, but what about -1 to the 4/2? On the one hand, -1 to the 4/2 is -1 squared, so it should be 1. On the other hand, -1 to the 4/2 is going to be the square root of -1 to the 4th. Okay, and so that's going to be undefined. I mean, we can talk about complex analysis if we want, but that's not my intention here. We're not going to do that in this course. Okay, so you have to be really careful when you have a negative value to a power. And here's something even more troublesome. How would you define -1 to the pi? What does that even mean? Okay, if you were to have -1 to the pi. It's tricky enough to talk about, say, 2 to the pi, which is a well-defined real number, 2 to the pi. Pi, as you know, is 3.14, 159.265, blah, blah, blah. But how can you define it? Well, one way that you can define it is by a limit. And with this limit, you could think of 2 to the pi as the limit of 2 to the x as x approaches pi, where you're considering you're considering only rational values for x. So you could think about, say, 2 cubed, or 2 to the 3.1, or 2 to the 3.14, and so on. And so the more values you add, okay, the more values you add to the exponent, the closer you get to 2 to the pi, and then you take the limit, and that's what it is. That's hugely troublesome for a negative base. Okay, and so that's going to be one of the issues that we're going to come across there. So to deal with that, we're just ignoring completely negative values of a, negative bases for the exponential function. We're only going to consider what happens when a is bigger than 1, and then when a is between 0 and 1. And of course, when a is equal to 1, this is a super boring function, right? It's just 1. 1 to the anything is 1, and that's it. Okay, so we're not going to talk about that. Nothing interesting happens there. Now, it actually turns out, for reasons that we'll explain, it's enough to understand what happens when a is bigger than 1. So we'll handle that. We'll go through that. So what I want to do is I want to think about the calculus part of this. I want to think about what's the derivative if we have f of x equals a to the x. Okay, what is f prime of x? And we don't really have any choice here except to talk about the limit definition of the derivative. And the limit definition of the derivative is, of course, the limit as h approaches 0 of f of x plus h minus f of x all over h. Okay, and in this case, we can factor out an a to the x because a to the x plus h is just a to the x times a to the h. So we can factor that a to the x out of the top. And x is independent of h, which is the variable in our limit. So we can actually bring that outside of the limit. And what we have left is we have to look at this limit of a to the h minus 1 all over 0. And of course, this is going to be 0 over 0, like all the interesting limits that we talked about in Calc 1 as well. And we have to think about what is this limit going to be. And it turns out that if I think about a being 2, So if I think about a being 2, if I look at 2 to the h minus 1 over h, and I take the limit as h goes to 0, you can play around with this a little bit, say on a calculator, and you can figure out that this limit is something like 0.7. It's about 0.693. Okay. And if you were to look at the limit, is if a is 3 as h goes to 0, this is going to be something like 1.01. Okay, something like that, a little bit bigger than 1. And if you were to look at the limit of 4 to the h minus 1 over h, that's going to be something that's a little bit larger still. Okay, I don't know the exact value, but it'll be a little bit bigger than 1. Okay, 1.2, 1.3, something like that. Okay, actually, it'll be 1.4 just about. Okay. Now, what this means is that if you look at the limit of a to the h minus 1, if you think of that about this as a function of a, then this is an increasing function. And the larger value of a you plug in, the larger value you get out. And when you plug in 2, you get a value that's about 0.7. When you plug in 3, you get a value that's a little bit bigger than 1. And I might have this number wrong, by the way. I'm just remembering. I can't remember if this is 1.01 or 1.1. What it really turns out to be, I'll just ruin the punchline. It really turns out to be the natural log of 3. Okay, and we'll go over that, exactly what that means soon. Okay, but the limit of a to the h minus 1 over h is increasing in a. So this is increasing as a function of a. And therefore, somewhere between 2 and 3, there's a value where this limit is exactly 1. Okay, so somewhere in the interval from 2 to 3, there exists a value. This is a really special number called e, but there exists a value e, which is about 2.718, where this limit as h approaches 0 of e to the h minus 1 over h is equal to 1. Okay, and the fact that it's equal to 1 makes it very special, because think about what this means. This means that if we were to take the function f of x equals e to the x, then the derivative would be e to the x times the limit as h approaches 0 of this e to the h minus 1 over h, which is just e to the x times 1. Okay, and so what this tells you is that e to the x is this very special number where the derivative of e to the x is just itself. Okay, so it's just e to the x. And again, e is this number 2.718. E is a number, it's named after a mathematician called Euler. Okay, so who was a Swiss mathematician in the 1700s, probably the most prolific mathematician ever. Okay, he wrote something like 1,500 math papers. He has so many different things named after him, but probably the first and foremost, the most important thing is this number e. Okay, and so this is the number e. It comes up absolutely everywhere. When we talk about applications, we'll see exactly how ubiquitous this number is. Okay, but it comes up in all sorts of places like finance, biology, physics, engineering, everywhere. It's just absolutely everywhere. Of course, math. So that's e to the x. E is the special number 2.71828, where the derivative of e to the x is itself. Okay, and this in a certain sense is the only function with that property. Of course, we could put any constant that you want in front of it, like 5 e to the x. The derivative of 5 e to the x is 5 e to the x, because you know how to deal with constants with derivatives. But other than that, this is the only function with that property. Okay, so up to that constant multiple in front. So that's how we differentiate e to the x. And with that, what we can do is we can also talk about the chain rule. So if you were to have the derivative of e to a function of x, say e to the g of x, the derivative is going to be that same thing, e to the g of x times the derivative of the exponent. So that's what the chain rule looks like in this case. So for example, if we were to have the function f of x is e to the 4x squared plus 7x plus 3, then the derivative would be e to the 4x squared plus 7x plus 3. So it's always itself. times the derivative of the exponent, the derivative of 4x squared plus 7x plus 3 being 8x plus 7. Okay, or if we were to have f of x as e to the tangent of x, then the derivative would be e to the tangent of x times the derivative of the tangent of x, which is secant squared of x. Okay, and so that's how the derivative of exponentials work. And also, the integral of e to the x is e to the x. Okay, so that should not come as a surprise. If the derivative of the function is itself, then the antiderivative of the function is also itself plus a constant. And so if I were to want to evaluate e to the 4x plus 1, then we could do a substitution. U is 4x plus 1, du is 4 dx. Divide both sides by 4. And this is going to be the integral of e to the u du times 1/4. And altogether, this will be 1/4 e to the 4x plus 1 plus e. Okay, and this is one of the places where mental arithmetic really will help you go a little bit faster through these. Okay, and so I think that's everything I wanted to say about exponential functions. There's one other alternative definition of e that I think I should share. So e is the value where, and this is how we defined it. I'm just going to write this to keep everything straight. But e is the value where e to the h minus 1 over h has this limit of 1. But you could also think of e as the following limit. If you take the limit as x approaches infinity of 1 plus 1 over x to the x. Now, there's a few different intuitive ways to think about this limit. As x goes to infinity, 1 plus 1 over x goes to 1, and 1 to the anything is 1. So I think intuitively it makes good sense to think of this limit as 1. On the other hand, 1 plus 1 over x is a little bit bigger than 1. And when we take that to an increasingly large power, that should get larger. And so I think you could think of this as being 1. You could think of this as being infinity. And both of those are good, reasonable guesses just based on intuition that both happen to be wrong. This limit happens to be, of course, e. Okay, so this limit of 1 plus 1 over x to the x is e. Okay, and again, we will look at this limit much later. Okay, so in the last section of chapter 6, we'll talk about something called L'Hopital's rule that'll really help us make sense of this limit. We'll prove that this limit is e. Okay, so there's a few different ways to think about this. This is actually the version that makes e come about from finance. So when you're talking about compound interest, this is the kind of quantity that you're looking at, and we'll get into that in due time. Okay, so we'll talk about some of those applications there. But I think that's everything that I wanted to say just from a theoretical perspective from chapter 6, section 6.2, I mean. And we'll do a lot more examples of differentiating and integrating in the Wednesday's lecture.